So picture this. You're stranded on an island and you come across this function, f of x, and he says to you, "Hello, sir or ma'am. I have been alone on this island for so long and I just want to know what I look like. So please sketch me." And so you're like, "Okay, I can do that. Let me get my calculator." But then you remember you're stranded on an island, so you don't have a calculator. So what are you going to do? What you can do is you can use all the tools you have in your Calc 1 tool belt to sketch this without the use of any fancy technology like a computer or a graphing calculator. So that's what we're going to do. We're going to go through all the steps of, it's called curve sketching, and I think that all these steps is a really great summary of the curriculum of Calc 1, right? It has like the majority of the things that you learned, you're going to be able to apply it to sketching this function. So we'll go through all the steps, and these steps can be used to sketch any function, not just this specific f of x. And we'll just do it one step at a time, and then we'll get a nice sketch by the end of it. So the first step that we're going to talk about is, let's discuss the domain of f of x. Okay, so in order to do that, let's look at the two parts that f of x is made up of. The first part is this 3x to the 5/3. And this exponent might be kind of intimidating, so actually let's just come back to that. The second part, x minus 8. So is there any restrictions on what you're allowed to plug into this part, x minus 8? No, you can plug in anything and you'll get an answer out of it. So the domain isn't restricted from this x minus 8. What about the 3x to the 5/3? So this you could think about as x to the power of 5, and then you take the cubed root of that. So a lot of times the square roots, cubed roots, whatever, those, maybe sometimes you can't plug in negative numbers. So for example, if this was x to the 5/2, then if you plugged in a negative number like -2, you'd get -2 to the 5th. That's a negative number, and then you can't take the square root of a negative number, but we're doing the cubed root. And so you actually can take the cubed root of a negative number. So there actually, if you think about it, there aren't any numbers you're not allowed to plug into here because you'll always get an output. Contrasting that to if this was a square root instead of a cubed root. So the domain actually has no restrictions. So the domain is -infinity to +infinity. What about any discontinuities? This kind of goes along with domain. What about any discontinuities? So that would be like vertical asymptotes or jump discontinuities or holes or anything like that. Does it look like there'd be any of those here? A vertical asymptote would be like if you have a denominator somewhere, and wherever that denominator of some fraction equals 0, that would be where you have a vertical asymptote, but there's no denominator. And also this is made up of two familiar functions, and each of these are continuous functions, right? X minus 8, that's continuous, and 3x to the 5/3 is also continuous. So the whole function f of x is therefore continuous, so there are no discontinuities. So the next step is we want to check and see if there's any useful symmetry in f of x. And so just to review, if a function has even symmetry, that means that f of -x equals f of x. So that kind of manifests in the graph as being able to fold the graph over the y-axis and then it lines up. So like, for example, y equals x squared, that is a even symmetric function. And then odd symmetry manifests when you determine that a function has odd symmetry when f of -x equals -f of x. And that would be like the function y equals x cubed. And you could think about this symmetry as like you take the right half, you fold it over the y-axis, and then you fold it over the x-axis. And if that lines up, then it has odd symmetry. So to check this for f of x, to check if it has even or odd symmetry, we're going to plug in -x. We're going to use these two formulas. We're going to plug in -x and see if we get f of x or if we get -f of x. So let's do that. So so let me scroll so that you can still see f of x. F of -x, we're just going to plug in -x everywhere we see an x. So doing that, we get 3 times -x to the 5/3 times -x minus 8. And now we got to simplify this and see if we recover f of x or see if we recover f of x just multiplied by -1. And then we'll be able to determine the symmetry. So here, this part is the tough part. So let's split this into 3 times -1 to the 5/3 times x to the 5/3. And then we'll keep this negative x minus 8. And then what is negative 1 to the 5/3? Well, that's negative 1 to the power of 5, which is negative 1 times negative 1 times negative 1 5 times. Since you're multiplying it by itself an odd number of times, it's going to be negative 1. So negative 1 to the 5th power, negative 1. And then we have this cubed root, right? So we have negative 1, the cubed root of it. And that would just also be negative 1. So this simplifies to negative 3x to the 5/3 times negative x minus 8. And so let's compare this to our original function. So this right here is f of negative x. And compared to f of x, which was our original function up here, f of x is just positive 3 times x to the 5/3 times x minus 8. So if you notice, it might look like f of negative x is just negative 1 times f of x, but because of this negative here, but we have this negative here as well in front of the x in x minus 8. So you can't just take f of x, multiply by negative 1, like up here, and get f of negative x, because there's this negative sign, but there's also this negative sign. And also it's clear to see that f of negative x right here is not the exact same as f of x. So this function has neither odd nor even symmetry. All right, so now the next step is we want to check for the asymptotes. So to do that, we actually kind of already discussed that there wouldn't be any vertical asymptotes when we determined that there's no discontinuities in the function. And remember, that's because there's no denominator that could potentially be equal to 0. So we're going to check for horizontal asymptotes. So let's say no vertical asymptotes. Okay, and so then now let's check for horizontal asymptotes. So now think about it for a second. Do you remember how to check what the horizontal asymptotes of a function are? The approach is that you want to, well, just first of all, think about what a horizontal asymptote means. If you have a horizontal asymptote of like y equals 2, that means that as the function gets as the x values get really large, as you move to the right side of the function, the values are approaching y equals 2. Or it could be as x values get really small and you approach the far left of the x-axis, the y values approach 2 in this example. So horizontal asymptotes are all about long-term behavior, like as x gets really big or as x gets really small. So we're going to solve for that by using the limit. So the limit as x approaches infinity of the function, if this is a finite number, then we know that the function converges and it'll have this horizontal asymptote. You also have to check though what happens as x gets really, really small, because that could also converge to a finite number. So as x approaches negative infinity. Okay, so let's solve for both of these limits. Neither of them are too difficult. The top one, both of them actually, you can just solve by sort of substituting in infinity. So this isn't like mathematically rigorous. So if any of you guys are like math PhDs or whatever, then just forgive me. But it's good enough to get the answer. So you can just like plug in infinity for x. So 3 times infinity to the 5/3 times infinity minus 8. What does that equal? Well, infinity to the 5th power is like infinity again, I guess. And then the cubed root of infinity is still infinity. 3 times infinity is still infinity. And then infinity minus 8 is still infinity. So you get infinity times infinity, and then infinity squared is infinity again. So the whole thing, basically, all that to say the limit is just infinity. But what about when x approaches negative infinity? Well, you can do a similar thing. So you just basically plug in negative infinity. So now we have negative infinity to the power of 5. That's negative infinity. And then the cubed root of that, that's still negative infinity. And then you multiply that by negative infinity minus 8. So okay, so this first term, 3 times negative infinity to the 5/3, simplifies to negative infinity. And then negative infinity minus 8 is, again, just negative infinity. So you actually have negative infinity times negative infinity, and the negatives will cancel. And so you just get infinity again. Hopefully that wasn't too confusing, but That's what the limits are. So since these limits didn't converge to a finite number, it means that there's no horizontal asymptotes. But knowing the actual value of the limit that it approaches infinity from when x is really big and when x is really small, that's actually important to know because we'll have our graph at the end and we know that as x gets really small, it's way up here in infinity. And when x is really big, it's way up here in infinity. So it'll like come down from both sides like this somehow. Anyway, so we can say that there are no horizontal asymptotes and no vertical asymptotes. Okay, moving along. The fourth step, let's see, what is the fourth step? Okay, so now we have to start taking derivatives and stuff so that we can determine on what intervals is the function increasing or decreasing, and we can also determine what the critical points are and check and see if they're local mins, local maxes, global mins, etc., etc. So first step, number 4. So 4 is called, we'll just call it like increasing, decreasing. So in order to determine this, like I said, we have to take the derivative of the function. So I've recopied the function here. And so now we got to find f prime of x. So what's the best approach for doing this? A lot of people might think, okay, well, it's a product of two functions of x. Let's just do the product rule. And while that's totally valid, you can do that. It might be a little easier to do some algebra on f of x to get it into a form that makes it easier to do the derivative. So for example, let's distribute this 3x to the 5/3, and then we'll just get a polynomial where each term we can just apply the power rule to get the derivative. So if I distribute this 3x to the 5/3, then what would we get? We would get 3x to the 5/3 times x, which is 3x. This is x to the 5/3 times x to the 3/3. So you're multiplying together these things with the same base, so you can add the exponents. So 5/3 plus 3/3, we get 8/3. And then 3x to the 5/3 times -8 is minus 24 times x to the 5/3. So this is the same function f of x, just rewritten in a way that's easier to take the derivative. So now let's actually do the derivative. Now you see how it's easier, we can just do the power rule. So now we'll do the derivative of each of these terms. So applying the power rule, we bring the exponent down and multiply it with this coefficient and then decrement the exponent by 1. So we'll get 8/3 times 3 is 8 times x to the power of 8/3 minus 3/3, right? 8/3 minus 1, so that would be 5/3. And then minus 24 times 5/3. The 24 and the 1/3 will become an 8, and then the 8 times 5 will become a 40. Do you guys see that? So this becomes 40x to the 5/3 minus 1 is 2/3. So there we go. We have our derivative. And now to find, the intervals where it's increasing or decreasing in the min and max, we got to set this equal to 0 and solve for our critical points, right? That's the definition of a critical point. It's where the derivative equals 0. It's also where the derivative is undefined, but you can tell from this expression for the derivative, it's never going to be undefined no matter what value of x we plug in. So our critical points are going to be where this derivative is equal to 0. So let's solve for that. And to do that, the best way I would recommend is by taking this expression and factoring out a greatest common factor. So let's do that. So let's factor out 8 times x to the 2/3, right? That'll be our greatest common factor. So 8x to the 2/3, when we factor that out, we get, this 8 gets factored out, so we just get x to the power of what? So 5/3, and we divide x to the 5/3, and we divide by x to the 2/3. So this becomes x to the 3/3, right? You can imagine distributing this back in, you would get 8 times x to the 2/3 plus 3/3, which is 8 times x to the 5/3. And then over here we took out an 8x to the 2/3 here, so this becomes just minus 5. And this still equals 0. And this is just, x to the 1, right? So I could have said 8 times x to the 2/3 times x minus 5. So now we have this product of two functions of x equals 0. So when either of these products equals 0, then the whole expression equals 0. So we can split this into two equations. 8 times x to the 2/3 equals 0, or x minus 5 equals 0. And when either of these two things are true, the whole function equals 0. So we have our two critical points now. X can equal, so when is this true? Only when x equals 0. So x can equal 0, or x can equal, from this guy, x can equal 5. So these are our critical points. So once we get our critical points, now we have to do our first derivative test, which is where we plug these critical points onto a number line of our derivative. So this is like, here's our critical point 0, here's our critical point 5. And we got to plug in values below 0, in between 0 and 5, and above 5 into our derivative. So we'll do that. So, and see if it's positive or negative. That'll tell us if the original function f of x is increasing or decreasing on that interval. So for values less than 0, let's go ahead and plug in f prime. Let's plug in -1 and see if that gets us a positive number or a negative number. The one I'm going to use is this version of f prime of x, just because it'll be easier to plug in the numbers. So we're plugging in -1. So a -1 here, let's just write it out. So here we go. I took this f prime of x, I rewrote it down here, and I plugged in -1 wherever there was an x. So here we have -1 squared becomes 1, and then the cubed root of 1 is also 1. So we have 8 times 1, that's a positive number, times -1 minus 5, that's -6. This is a negative number. So this is positive times negative. So the end result will be a negative number. Okay, so up here I'm going to put like a negative sign. So every number before 0 has a negative derivative, meaning the original function was decreasing on that interval. So now let's plug in a number between 0 and 5. Let's just do f prime of 1. So f prime of 1. So here we have 1 squared is 1. The cubed root of 1 is also 1. So we have this positive number times 1 minus 5 is -4. This is a negative number. This whole thing is going to be positive times negative, so negative. Which is weird, right? Normally you're used to seeing it change from negative to positive, but it certainly doesn't have to. It just means that 0 doesn't correspond to a local min or max. So then let's test anything greater than 5. So let's do like f prime of 6. Then we would get 8 times 6 to the 2/3. That's going to be a positive number. Times 6 minus 5. That's also going to be a positive number. So this whole thing is positive. So we can say any value greater than 5 has the derivative being positive, meaning the original function is increasing. So we found our intervals now. So we can say f of x is increasing from 5 to infinity and decreasing from -infinity to 5. Okay, there we go, there we go, there we go. And another thing we can say is that since the function went from decreasing to increasing at x equals 5, that means that x equals 5 corresponds to a local minimum of the function. So x equals 5 is a local min. Also, interestingly, you could say that x equals 5 is also a global min, because we know from up here, dang, where was it? We know from up here that the function goes from infinity on the far left and it goes to infinity on the far right, like up here when I sketched this. And so then it goes down like at x equals 5. This is 5. We have like a minimum down there. So we know that it's a global min as well. On the entire, it's a minimum on the entire domain of the function. So it's also a global min. Okay, so the next step is we want to talk about concavity. So we just talked about increasing or decreasing, which uses the, is this step 5? Yeah. So increasing, decreasing uses the first derivative, and then concave up, concave down is like the second derivative analog. So now let's discuss concave up, concave down, question mark. And we can also discuss where are the inflection points. An inflection point, as you know, is just like a critical point, but for like the second derivative. So it's where the second derivative is 0 or undefined. Okay, so to do this, we got to get our second derivative of the function. So let me recopy down the first derivative. Okay, I recopied down the version of the first derivative that isn't factored out, just because it'll be easier to take the derivative. So given that this is f prime of x, f double prime of x is gonna, we just do the power rule. So 8 times 5/3, that's 40/3, times x to, and we subtract 1 from this exponent, so 5/3 minus 1 is minus 3/3, so we get 2/3 is the exponent, and then minus 40 times 2/3, so that's 80/3, times x to the 2/3 minus 3/3 is minus 1/3. Okay, so now we want to find all the inflection points, so let's set this equal to 0 and solve for x. Or the inflection points are also where the second derivative is undefined, but you can see this is never going to be undefined. So let's go ahead and try to solve this equation. I'm going to use the same approach as we did for the first derivative, solving for when it equals 0. We're going to factor out a GCF, a greatest common factor. So that would be 40/3 times x to the minus 1/3. So when I factor that out, what am I left with? So here we get x to the, this 40/3 got factored out, and we factored out a minus 1/3. So this is just x to the 3/3, right? Imagine distributing this back in. You would recover 40/3 times x to the 2/3. And then here we go, we have a minus 2, and then this x to the minus 1/3 got factored out already. So this is actually, this 3/3 up here is actually just 1. So I'm going to erase that if I can. Okay, so then we set this equal to 0, and then we solve for our x value. So this is where either this is equal to 0 or where this is equal to 0. So then we can get our answers for the inflection points. X is equal to 0 or 2. Okay? Boom. So now we do the same thing we were doing with the first derivative, but we do it with the second derivative in order to find the intervals where the function is concave up or down. So we plug in 0 and 2. This is a number line of the second derivative of x. And then we just start plugging in some numbers. So like f double prime of -1. What is that? So I'm using this version of the second derivative just because it's easier to play with the numbers and just decide if it's like positive or negative. So I plugged in -1 into here. And so I got that this is, okay, so -1 to the -1/3, that's 1 over the cubed root of -1, which is 1 over -1. So this is negative times, this is -1 minus 2. So this is also negative. So we have a negative times a negative. This is going to be a positive number. Okay, so in this interval, -∞ to 0, we have concave up. So then let's plug in something in between 0 and 2. So f double prime of 1. What is that? So we have 1 to the power of -1/3. So that's 1 over the cubed root of 1, which is 1 over 1, which is a positive number, times this positive number. So this left part is positive. And then we're multiplying that by 1 minus 2, which is negative. So in the end, we get a negative number. So in this interval, 0 to 2, our second derivative is negative, so the function is concave down. And then now we just got to check something greater than 2. So let's do like f double prime of 3. So here we have 3 to the -1/3, which is 1 over the cubed root of 3, which is 1 over a positive number. So this whole thing is positive. And then we multiply it by 3 minus 2, and 3 minus 2 is positive. So we have a positive part times a positive part. So in the end, this is a positive number. So the interval 2 to infinity, we're concave up. All right, and then these are our inflection points. So what's left to do? Are we done yet? Finally? Let me see. We have one more step. And the last step is let's figure out, this is step 6. So let's discuss x and y intercepts. Okay, so let's see, the x-intercept is where y equals 0, right? It's where the function pierces the x-axis. And it does that when the y value is 0. So the x-intercept is where y equals 0. So we can say this is where the function 3x, this is the original function I'm writing, 3x to the 5/3 times x minus 8. The x-intercept is where that function evaluates to 0, right? That's where it'll cross the x-axis. So when is that true? That's true when this part is equal to 0 or when this part is equal to 0. So our x-intercepts are where x equals 0 or 8, okay? And then y-intercept is where x equals 0, right? It's where it pierces the y-axis, which happens when your x value of the function is 0. So then we can just plug in x equals 0 into the original function. So doing that, we get 3 times 0 to the 5/3 times 0 minus 8. What is this equal to? Well, this is just 0 times -8, so this is just 0. So the y-intercept is at y equals 0. So x equals 0, y equals 0. So the point 0, 0, right? Okay, so we're done now. So I'm going to make a little summary of all of the info we got from all these steps, and then after I do that, we'll talk about how you can use all that information to actually graph or sketch the graph of f of x. Okay, so we put in a lot of hard work into figuring out as much as we could about this function using just our minds, right? We didn't have to use any of that fancy tech. Anyway, I've summarized it all here. And so now I have this xy plane, and so let's try to sketch the function. So let me just rewrite this so that we can appreciate what we've done. Okay, so we have this function f of x that's like a pretty complicated function. And now we actually have the wherewithal to graph it without, any special tech like computers or graphing calculators. And that's cool, right? I mean, before I took Calc 1, the only functions that I would know how to sketch on my own would be like just y equals 2x plus 3, or like y equals x squared, but something this complicated I would have never been able to do. But look at all this information we gathered about this function. It's going to help us graph it, and we're going to be able to do that just wearing our good old-fashioned Calc 1 tool belt. So let's actually sketch this thing. So we know that it doesn't have any symmetry, so we're not going to just be able to draw one half of it and then use symmetry to draw the other half. We have to sketch the whole thing. But we have all this other information. So we know it goes from, it's going to come down from positive infinity on the left and go off to positive infinity on the right. And we know that the y-intercept is 0, 0. So we're going to have a point here. And from negative infinity to this point, we are going to be decreasing, and we're going to be concave up. So it's going to be kind of curving up as it comes down. So, but then also an interesting point is that at the point x equals 0, it switches from concave up to concave down. So it's going to go from curving up to curving down, kind of like that. Do you see it? Kind of like the graph of x cubed. So we're up here at infinity, we're concave down as we decrease to 0, and then at 0 it goes from concave up to concave down. So then we become concave down at that point, but we're still decreasing, right? We decrease until x equals 5. So at 5, we actually have at x equals 5, we're going to have a minimum, because that's when it stops decreasing and starts increasing. And also at x equals 2, we're going to switch from being concave down, so we're going to switch from curving down to curving back up again. And that kind of makes sense. It has to start curving back up again if it's ever going to flatten out. So we go and we're concave down, but then at 2 we start curving back up, and then we go flat here at x equals 5, because that's where we stop decreasing and start increasing. And then from x equals 2 until infinity, we're concave up, so we keep curving up, curving up, curving up, until we cross the x-axis again at x equals 8. So here's 8. So then we're still concave up, increasing, increasing, increasing. We cross the x-axis at x equals 8, and we just keep on increasing forever. And we go off to infinity on the right. So here's our first draft, right? I always kind of just recommend you get a first draft out there and then go back and review, make sure you didn't miss anything. Let's just verify. It's not symmetric. It goes off to infinity on the far left and the far right. The y-intercept is 0, 0. The domain is negative infinity to positive infinity with no discontinuities. We cross the x-axis at 0 and 8. We're decreasing from negative infinity all the way to 5. That makes sense. And then we increase from 5 to infinity. We're concave up from negative infinity to 0, so we're curving up all the way until 0, but then we start curving down until only 2, and then we curve up the rest of the way. And then there are no asymptotes. The way I drew this, it kind of looks like there's a vertical asymptote here, but it's just because I'm bad at sketching. Really, it should just be increasing forever with not approaching a certain x value, But yeah, so this looks good. So this is the graph of f of x, and I hope that you feel more confident in your Calc 1 abilities. So now, yeah, if you're ever stranded on an island, you can sketch a function. Okay.